Hello everyone, dear participants of the 8th International Workshop on Computer Modeling and Intelligent Systems. I would like to present my research analysis of methods and implementation of a modern technology stack for increasing the productivity of websites. I'm Ivan Stepa. I work at the Department of Computer Science in Zaporizhzhia Polytechnic National University. As you know, web technologies have become crucial for modern life, driving interactive solutions in various areas. With the growing data, user bases and performance needs, a scalable and optimized architecture is essential. This project uses Node.js, Express.js, and MongoDB to build the fastest website, focusing on scalability and performance under heavy loads. It leverages the MVC architecture PM2 for server management, Quartz for secure APIs, and Mongoose for database interactions. Uh, the research also covers strategies for managing complex data and boosting interactivity. So let's describe our problem.
One of the indicators of the website is the loading speed, which depends on many factors. In this study, the authors hypothesize that the use of modern technologies such as Node.js for server-side request processing and MongoDB for data storage will lead to a significant improvement in the performance of web applications under high loads. The architecture of a web application, in particular, the use of the MVC pattern affects its scalability and the request processing speed. It is expected that the use of MVC architecture together with clustering using PM2 will reduce response time and increase the ability of the system to process simultaneous requests as well as provide security through cores. Uh, at this slide, you may see page load times. According to this slide, the probability of abandonment increases by 32% when your page load time increases from 1 to 3 seconds. According to Google, the probability of abandonment, that is when visitor leaves your site without taking action, increases by 32% if your web page load increases from 1 to 3 seconds. Moreover, it increases by 19% from 1 to 5 seconds. From 1 to 6 seconds, it increases by 106%. And from 1 to 10 seconds, it increases by 123%. The conclusion from this is clear. If you want to keep visitors on your website and convert them, it's important to minimize page load.
What we do in Node is running multiple Node processes side by side, allowing them to share the work among themselves like a team working together to achieve a common goal. With servers, the work that is being done is broken down into requests that come to the server. Therefore, instead of taking each request and processing it on a single Node.js server using a single node process, we can distribute the requests across multiple Node.js processes. Each of them will respond to the request in the same way. Each of them contains a copy of the server code that runs in parallel side by side. Now this second request can be handled by a second node process, and the third request can be handled by a third node um, process. In addition, if we have more requests than servers, each of these processes can be still handle multiple requests at the same time. The important thing is that they now share the load equally among themselves. Using this technique allows single-threaded node applications to take full advantages of all processors on a computer. Um, at this slide, you may see CPU multi-threading demonstration. It shows that the most computers today have multiple processor cores that can execute code in parallel, taking, um, without affecting the performance of code running on any other processor core. Our first approach to improving node performance is to use the built-in node cluster module. The cluster module allows you to create copies of your code process, each of which executes server code in parallel side by side. Um, figure This figure shows how this works as allows. When a node type is entered, the server agrees to run the node application, and a main node process is created. Node calls this the master process inside the cluster module. We have access to the function called fork. Whenever a worker function in the server file is run, node takes this master process and creates a copy of it, which it calls a worker process. We can call this function for. However, we often like to create many worker processes attached to a single master process. This slide presents the Node.js cluster module architecture, main process, and worker process. The figure illustrates the process when the server runs a node application, master process is created. Using the fork function, the master spawns the worker processes which handle HTTP requests. Each worker manages server requests while the master coordinates their creation. Um, in this setup, running the worker function twice results in three processes: the master and the two workers, distributing requests in a round-robin fashion. Although round-robin is set simple and fair on Windows, Node.js relies on the operating system for task distribution, but round-robin can still aid in load balancing. Cluster has its limits. Let us do another little experiment, continuing the example with two more tabs open. At this slide you may see experiment temporary cluster shortcoming. The figure shows each tab with the network console open and cache disabled when accessing the timer endpoint simultaneously. The first and second tabs return responses after 9 seconds. A request to the root endpoint took 6.5 seconds, and the last timer request took nearly 16 seconds, and only two requests were proceeded in parallel. The other had to wait due to blocked processes. The process IDs show a round-robin approach, with the third and fourth queries reusing the first and second processes. Clustering isn't a universal solution, and it's limited by number of processes running in parallel. Our current setup handles two requests simultaneously, requiring more workers for additional requests. Efficient worker creation involves automating forks based on the system's available processors, ensuring each process uses a separate CPU core.
Clustering demonstrates significant advantages, for example, parallel execution of long-running and fast requests without mutual blocking. However, during testing, it is necessary to disable the browser cache so that the requests are actually executed simultaneously. The results shows that separate processes, which significantly increases the server response speed, process different requests. However, in real conditions, it is important to configure clustering correctly to achieve optimal performance. Therefore, when testing server clustering, we need to disable the cache so that Chrome actually executes requests. We need to disable the cache in both tabs. Let's make two requests in one tab to our timer endpoint and very quickly refresh the first and second tabs. At the first part of the slide, you may see parallel processing of timers using two physical cores. Uh, Figure shows that in the first tab we see that the connection is waiting. We wait 9 seconds, and here we have a response to 100. This is successful. Moreover, at the same time, the response is received in the other tab. Both requests took 9 seconds. They were executed in parallel on the computer because it has two processor cores, and they were processed in two separate processes. Um, at the second up lower part of our slide, you may see comparing the root tab and the timer tab for performance at the same time. In this figure, we make a request to the timer endpoint in one tab and to the root directory in another one. And the request to the root directory returned almost instantly after 27 milliseconds. The root and point here do not have to wait for the timer to finish in the first step. This is exactly what we needed.
We aim to limit the number of workers to the CPU's logical or physical cores. Physical cores are individual processors running in parallel, while logical cores use advanced logic to run multiple threads on one core, uh, though less efficiently. To optimize server performance, we match the number of workers to the number of um, logical cores using the OS module with 4 physical and 8 logical cores. We create 8 workers, allowing up to 8 simultaneous browser requests, enhancing performance. 4 physical cores handle requests in about 9 seconds, while the remaining logical cores provide intermediate efficiency. At this slide, you may see parallel processing of 8 tabs simultaneously in 9 seconds. In this figure, we see total 8 requests were made. Let us make sure the cache is disabled. Again, about 9 seconds. This is indication of efficiency of the logical cores on the computer. The server performance was maximized based on the number of CPU cores on the computer.